Now, on an homogeneous second order ODE, use the D factor method to solve the differential equation d squared y over dx squared minus 4dy over dx plus 4y is equals to exponential 2x. Now, if you look at this, there are no boundary conditions, isn't it? You've not been told when x is this, y is that, and dy over dx is that, meaning there's no boundary condition. So if there's no boundary condition, it means we are looking for the general solution of this second order non-homogeneous ordinary differential equation. So how do we get the general solution of this? Using the D operator method. How do we use the D operator method to find the general solution of this non-homogeneous second order ordinary differential equation? So we know for you to use the D operator method, you let y to be equals to u plus, you let y to be equals to u plus v. So it means this equation we have here is going to be divided into two parts, isn't it? The first part, y is going to be v, and the second part is going to be, the first part is going to be u, and the second part is going to be v, isn't it? So there we have, the whole problem is d squared over dx squared y is u plus v, then it is minus 4 d over dx of y is u plus v. We are substituting the value of y, isn't it? Meaning where there is y, we put u plus. We have y here, we placed u plus v. We have y here, we placed u plus v, isn't it? We also have y here, so we are going to have 4, then u plus v to be equals to exponential 2, isn't it? Now if you look at this, it means when you divide the first part of this differential equation is going to be for u, isn't it? So can you now separate the u on its own and the v on its own? So here is going to be d squared u, isn't it? D squared u over dx squared, then minus 4 du minus 4 du over dx. We are collecting u's, isn't it? Then it is plus 4 times u plus 4u. So that is u part. Then it is plus the v part we have. The v part we have d squared over dx squared v, isn't it? So it is going to be d squared v over dx squared minus 4 dv over dx plus 4v, isn't it? Plus 4v. Then the whole of that is equals to exponential 2x. So exponential 2x, we say we write as 0 plus exponential 2x, meaning the first part we are going to compare with 0, and the second part we are going to compare with exponential 2x. Are you seeing that? So you can see the equation has remained the way it was. It was d squared y over dx squared. So where there is y if you put v, where there is y if you put u, you can see that same equation remains the way it is. You substitute y with u, isn't it? And you can see where there is y if you put v, that same equation remains the way it is, isn't it? Where there is y if you put v. So it is the sum of the two because y is u plus v. That is the easiest way to expand it and collect the terms which are similar. So in that order, the first part you compare to 0, forming the non-homogeneous ODE, and that non-homogeneous ODE is going to give us the complementary function. Are we together? The non-homogeneous ODE, which is in terms of u, this first part, which is d squared u over dx squared minus 4 du over dx plus 4u. This first part of the equation we compare with 0 is equals to what? Are we together? So this is the equation 1. Then equation 2, the second part of the equation is what? d squared v over dx squared minus 4 dv over dx plus 4v. We compare with the function f of x, and the function f of x was given as exponential 2x, isn't it? So this one is equal to exponential 2x, forming equation 2. Are we together? So equation 1 gives us the complementary function, and the equation 2 gives us the particular integral, isn't it? Then now the solution is y. Y is the complementary function plus the particular integral. Are we together? So let us start with the first part, the complementary function part. So the complementary function part, what do we have? The CF part, what do we have? We have d squared u over dx squared, equation 1, isn't it? Minus 4 du over dx plus 4u is equals to 0. So we are now using the d operator, isn't it? Meaning you let d to be d dx, because we are differentiating with respect to x, isn't it? This will imply that d squared will be d squared over dx squared. So where we see d dx, we put d squared over dx squared, we put d squared, isn't it? Yeah. So here we have d squared over dx squared is going to be d times the u which is here, isn't it? So this d squared over dx squared is d. So this times that u, so it is du, isn't it? Are we together? D squared u, I mean, that is d squared u, okay? Then you go here, minus 4, then d dx is d, then that u is there. So it is 4 du, isn't it? Are we together? Then you move on, plus 4u is equals to 0. Then from here, we get the auxiliary equation. We get the auxiliary equation by letting d to be m, isn't it? Now we do what? We let d to be m, so that we are able to get the auxiliary equation. Because when it is ddx, this derivative cannot be solved quadratically, so we have to let it to be another unknown to form the auxiliary equation, isn't it? So where this d you put m, meaning here we'll have m squared u minus 4mu plus 4u is equals to 0. Where this d you put m, so we have m squared mu, isn't it? So you can see u is a common factor. If you factorize out u, we remain with m squared minus 4m, u is common, plus 4 is equals to 0. So either u is equals to 0 or what? Or m squared minus 4m plus 4 is 0. So remember, when u is equals to 0, it means the differential equation does not exist there, isn't it? Are we together? So this is now the complementary function. So we now solve for m, isn't it? If we solve for m using quadratic formula, we have m is minus b plus or minus square root of b squared minus 4ac over 2a. You must always use quadratic formula because you can get m to be either two real factors, either to be two real or complex or real and complex, isn't it? Yeah. So always use the quadratic. First solution of m solve this, whether it's b negative 4. So negative or negative 4 should be positive 4. Positive 4 plus or minus square root of b squared. Negative 4 squared is 16. That is going to be 16 minus 4ac. 4 times 1 is 4 times c is 4 minus 16, isn't it? Over 2a over 2 times 1. So if you work out that, what you get to be m? 16 minus 16 is 0, isn't it? So you get m is equals to? M is equals to 2, meaning there is only one real solution, isn't it? Are we together? Yes. So if there is one real solution, what is our complementary function? When there is one real solution, then we have a plus bx into exponential that real function. Are you seeing that? Yes. Are we together? Yes. See, it is supposed to be a plus bx exponential m1x. If your solution here m is only one real solution, this is the form of the complementary function as we saw in our non-homogeneous, isn't it? Are we together? Yes. Because we have one real solution. So one real solution is in the form a plus b x exponential 2x, where that 2 is the only real solution we found, isn't it? Are we together? Good. Now, after getting the complementary function, we now want to get the particular. Are you seeing what we now want? The particular integral. So how do we get this particular integral? So we have the complementary function here. So let us come here and write the particular integral. So the particular integral is equation 2, isn't it? So equation 2 we have d squared v. This is where we are going to get the pi, the particular integral, isn't it? D squared v over dx squared minus 4 dv over dx plus 4v to be equals to exponential 2x. And we see we are now, this was equation 1 giving us complementary function. This is the equation 2 giving us the particular integral, isn't it? Yeah. Then now our solution is y is equals to u plus v, where u we found is the complementary function. Now we want to look for v, the particular integral, isn't it? Yeah. So you know v, the particular integral, it is the differentiation we are dealing with. So what is the choice of v? You have to choose v. V is what? You choose v based on the function f of x. What is the function f of x in this problem? Exponential 2x, meaning you are going to let v to be k exponential 2x, where k is a constant, isn't it? Are we together? You check the function. The function is exponential 2x, so it means we are going to choose k exponential 2x, isn't it? Then after you choose this, you check the complementary function. Is exponential 2x in the complementary function? Yes, because you can see this is a times exponential 2x. The exponential 2x is there. So you don't choose it. What do you do now? You add x to it. Are you seeing that? Are we together? You check again. Is x exponential 2x in the complementary function? You don't check the constant, you don't use while checking. Are you seeing that? Is x exponential 2x in the complementary function? You check again. See, this is bx times exponential 2x. Because exponential 2x is a common factor outside, isn't it? See, now there you have x exponential 2x. Meaning it is there. So if it is there, you add another x. So it becomes x squared. Are you seeing that? Then you check again. Is x squared exponential 2x in the complementary function? No, it is not there. Are you seeing that? So when it is not there, it means that is what you choose v to be. Have you gotten that explanation? Yes. The choice for v, you start from the function in the particular integral, in that part. You start with the function exponential 2x. Then you found when it is exponential 2x, meaning we are choosing k exponential 2x. Then we start checking what I've chosen. Is it in the complementary function? Are you seeing that? When it is there, you add x to it. You check again. Is it in the complementary function? Yes. You add another x, so it becomes x squared. So when you check that, is it there? No. So that is now the choice of v. Are we together? Are we together? Good. So from there you now start. We now know what v is. Now what do we want? We want the v over the x, then we have d squared v over dx squared, isn't it? So let us start. What is the v over the x? We differentiate, isn't it? See, we have v. See, for us to get the v over the x, we differentiate. So this is product rule, isn't it? Isn't it? So product rule, k is a constant you put outside. So it means when you take x squared step, you differentiate exponential 2x, isn't it? Meaning there we are trying to say your u is x squared. If you differentiate u, you get 2x, isn't it? And your v is exponential 2x. If you differentiate v, you get 2 exponential 2x. Because differentiating exponential 2x, it remains the way it is. You differentiate the inner function 2x, you get 2, isn't it? So the product rule, you know, you are supposed to have uv plus uv. If this is u prime, the other side is v prime, isn't it? So you just go u prime times v, 2x times exponential x, meaning you are going to get 2x exponential 2x, isn't it? Then it is plus uv prime. U is x squared, v prime is 2 exponential 2x, isn't it? So x squared times 2 exponential 2x, you get 2x squared exponential 2x. Are you seeing you differentiated that? Yes. Are we together? Product rule. So from there, you have dv over dx is equals to, you take k inside, it is 2k exponential 2x plus 2k x squared exponential 2x. K multiplies all the terms inside the bracket, isn't it? So here we found dv over dx. What else do we need? D squared. Are we together? So remember, one thing you need to know, what were we looking for? We were actually looking for the general solution of this second order non-homogeneous ODE, isn't it? And what have you noted? There were no boundary conditions. These ones I'm just using for explanation. There were no boundary conditions, isn't it? So if there were no boundary conditions, what does that imply? Plus? Nobody. Okay, let us go on. What is d squared v over dx squared? What do you get? You are differentiating for the second time. I will answer that later. What do you have there? Differentiate this part. If you differentiate this part, what do you have? It is product rule. You can, 2k is a constant, you can factorize 2k outside, then we differentiate x exponential x. It's 2x, isn't it? If you take x step, you differentiate exponential 2x, you get 2 exponential 2x. So there you are going to have 2x exponential 2x plus, if you now take exponential 2x step, you differentiate x, you get 1, you remain with exponential 2x, isn't it? Are we together? Yes, that one is this first part. Then you go to that part, this plus, you take 2k outside, then you differentiate x squared exponential 2x. Differentiating x squared exponential 2x is the same as what you got here, isn't it? Which was 2x exponential 2x plus 2x squared exponential 2x. Are we together? Now after this, you now take them back in the equation, isn't it? You take them back in that. We have d squared, this where it is, you substitute with this value, which is what? Open this bracket, 2k times that, you get 4kx exponential 2x, 2k times that, plus 2k exponential 2x, isn't it? Yeah. Then it is plus 2k times this, it is 4kx exponential 2x, then 2k times that, plus 4kx squared exponential 2x. So we substituted this, isn't it? So the whole of this is d squared v over dx squared. Then it is minus 4 into dv over dx. Minus 4 into dv over dx. Are you seeing dv over dx? So we multiply it by 4. Are we together? We multiply it by negative 4. Negative 4 is a common factor of everything, isn't it? Are we together? So negative 4 times this, negative 4 times 2, so you get negative 8. You get negative 8k x exponential 2x. Negative 4 times this, so you get negative 8 again. Negative 8k x squared exponential 2x. Are we together? We are done with this. Then it is plus 4v. 4 times v. What is your v? See, v is this. So it is 4 times v. So 4 we multiply by v, isn't it? 4 times this, you get 4. It is plus 4k x squared exponential 2x. So the whole of this equation is equivalent to what? Exponential 2x. Now look here. Now there is where I want to pay you to pay attention, okay? Look at this. You only compare the ones which are having exponential 2x only, isn't it? See, that is what we have on the right. Exponential 2. So you can see this term has k exponential 2x, meaning we don't need to use it because it is not on the right hand side of the equation. Are you seeing that? What is on the right hand side of the equation is this, we have 2k exponential 2x because 2k is a constant. It's the same exponential 2x exponential. We can compare that coefficient. Are you seeing? You go to this, there's x. There's no x here, we don't need that term. Are you seeing that? You move to this, there's x squared. There's no x squared here, we don't need that term. Are you seeing? Then you go to this, there's x. There's no x here, we don't need that term. Are you seeing? Then you go here, there's x squared. There's no x squared here, we don't need that term. Are we together? Then you go here, there is x squared. See, there's no x squared, we don't need that term. So which term do we need here? See, only that. Are you seeing how it is easy to live in Gaza? So here we have 2k exponential 2x to be equals to exponential 2x, isn't it? Good. So that is what you compare. What is on the right is what you compare. Here we have x exponential 2x. There is no x exponential 2x on the right. We don't compare that, okay? You only compare what is on the right. Is that understood? Good. You only compare what is on the right. And only this exponential 2x. 2k is a constant. Meaning that constant 2k is the same as this constant 1 here, isn't it? So we only compare the coefficient. Meaning this coefficient positive 2k is the same as 1. Because those are the coefficient of exponential 2x, which is what we have on the right. These other ones are x exponential 2x, x exponential 2x, x squared, x squared, x squared. We don't need those, isn't it? Are we together there? Good. Now having noted that, so what is the value of k? Because you have 2k is equals to 1, so you will get k is a half. Very simple. 2k is equals to 1. You are only comparing the coefficients of exponential 2x. Is that okay? So you get that 2k is equals to 1, so you get k is a half, isn't it? So we found v, which was, first of all, we found 2k exponential 2x. We compared it with exponential 2x on the right, isn't it? Meaning the coefficients of exponential 2x, this cancels with this, you remain with the 2k is equals to 1. We are simply comparing the coefficients, okay? So if you divide both sides by 2, then you get k is a half, isn't it? So after getting k, what is v? The particular integral. K x squared v is a half. X squared exponential. See where there is k, you put the value of k. A half. So we found v. So after finding v, we've also found we found u. What was u? See, u was here. We found u to be a plus bx exponential 2x. So we found both v and u. So having found both v and u, we can now get the solution. The solution is y, which was u plus is y, which was u plus v, isn't it? So you get y is, what is u? A plus bx exponential 2x, then it is plus v, which is plus a half x squared exponential 2x. And you have solved the second order non-homogeneous ordinary differential equation using the D operator method. Are we together?
Yes.
So you see, when you are given the initial conditions, you will now use those initial conditions to get rid of the constants A and B. When you are looking for the constants A and B, isn't it? But here we were looking for the general solution. There were no initial conditions, isn't it? Are we together? Very good. So have you seen how second order non-homogeneous ordinary differential equation is easier to deal with, isn't it?